This video provides a brief introduction to thermal analysis through the example of a bar element. Basically what we're going to do is compare the thermal analysis process to the stress analysis that most of these videos focus on. And then we'll briefly introduce the idea of doing a thermal stress linked analysis, and then finally do a simple bar element thermal example. The basic formulation of thermal FEA looks very similar to stress analysis FEA, except here the K represents a conduction matrix, and the degree of freedom vector has nodal temperatures rather than nodal displacements, and the load vector is consisting of heat fluxes rather than forces. But the formulation again looks very similar. Let's take a look at that conduction matrix. It is made of two parts, and the first part looks very similar from stress analysis. In fact, it's the same formulation as stress analysis. We've got B transpose times D times B integrated over the volume of the element. Here, D represents thermal conductivity. So again, it's a material property, but rather than being the elastic properties of the material, it's the thermal conductivity of the material. And that's going to be given in a 2D problem just by Kxx, Kyy as a diagonal matrix. The B represents the temperature gradients, so the derivative of the temperatures as a function of position. The formulation for that, again, looks identical to what we saw in the stress analysis. B is equal to the partial derivative matrix operator acting on the shape function matrix. And again, similar to what we saw in stress analysis, in a 1D problem, the partial derivative matrix operator is just d by dx. However, the conduction matrix also has a second part, and this second part comes from convection. Because convection depends on the surface temperature of the item, that surface temperature is initially unknown. Those are the nodal temperatures. So the conduction matrix, the way FEA is formulated, the unknowns are all on the left side of the equation. So the portion of convection that involves the surface temperature of the part shows up in the conduction matrix. Here we have the convective heat transfer coefficient H and the shape function matrix N, where we are integrating over the surface of the part that is exposed to convection. The right-hand side of the equation, the nodal load vector, is made up of, well, initially there's a distributed piece of that, and then there are point loads. So the distributed piece is made up of three parts. You've got heat sources, heat fluxes, and convection. This is the other half of the convection equation where we're looking at the far field temperature T infinity. So again, as a reminder, any point heat fluxes, point loads are going to be added at the assembly step, not as part of this distributed elemental nodal force vector. Let's take a look at the solution process for thermal FEA. In other words, what happens when you click Run on a thermal model? Turns out this process is very similar to what we have in stress analysis. First off, you determine the elemental properties, those matrices, so the conduction matrix and the load vector for each of your elements. Then you have an assembly process. You assemble all of the conduction matrices for each element to get a global conduction matrix, and you assemble the element load vectors together with the point loads to get a global load vector. Then you apply your boundary conditions. Instead of known displacements, these are now known temperatures. Then you solve for any remaining nodal temperatures, so your unknown degrees of freedom. Once you have all your unknown degrees of freedom, you can go back and find your reactions. The reactions at the boundary conditions are called heat fluxes in a thermal analysis. And then you find your element temperature gradients. These are analogous to your strains in a stress analysis problem. Now let's work through a quick example of the thermal FEA process applied to a simple model so we can solve it by hand. Imagine that you've got a bar or a fin that's insulated all along its edges. The left end, we're going to have a constant temperature of 100 degrees C, and we have a heat flux coming into the right end. We've got thermal conductivity for the material and cross-sectional area, and we're looking for the temperature inside of the bar, specifically at the right end of the bar, midway through the bar, and at each of the quarters. Well, given these dimensions, what makes the most sense is to break this into 4 elements, so that we have a node at each location that we're looking for temperatures. That way we don't have to do any interpolation at the end. So my 4-element model is going to look like this. Once I have a model defined, I want to go and find the element properties. And the first property that you're going to look for is the conduction matrix. So K is given by the formula shown here. The B and the N that we're going to find for thermal analysis for a bar element are identical to the ones we use for stress analysis. And this is because the partial derivative matrix operator is the same. And typically for a thermal analysis, we're going to use a linear temperature field, just like we used in a bar element a linear displacement field. So B and N are the same. So that means that my B matrix is minus 1 over L and 1 over L for the left-hand term there. For the right-hand term, the convection piece, pardon me, there is no convection in this problem because it's insulated along its length, so that term just goes to 0. Multiply things out and I get an element stiffness matrix that looks remarkably similar to the one that we have for the bar element in stress analysis. Plug in the terms, the length and the cross-sectional area, as well as the kxx, the thermal conductivity that was given, and we get a matrix that is going to be the same for every element because each element in this case is going to be identical. Let's look at the distributed force or the distributed load vector. In this case, it is simply 0 because we have no distributed heat fluxes in any of these elements. We have a point heat flux on the right side, Q, and we have an unknown heat flux on the left end in order to maintain my boundary condition of T equals 100 degrees C. Now that I have my element conduction matrices, I can put them together and get my global conduction matrix. So again, every element has this same conduction matrix. So to put it together, I'm going to get a conduction matrix, a global conduction matrix that looks like this. How did I get there? Well, it's a matter of stacking these up. Element 1 goes in the upper left corner. Element 2 is next, element 3, and element 4. This corresponds to each of those temperature terms that are at the nodes. So T1 is at node 1, T2 node 2, and so on. Just as we've done for the assembly process for a stress analysis FEA. But we're not done yet. We need to look at that global force vector. Again, we had no distributed terms, but we do have 2 point fluxes going on. On the right-hand side, Q times A is the flux that's coming in. And on the left-hand side, we have an unknown flux. I'll call it F1 that's maintaining my temperature of 100 degrees C. Plug in the Q and the A, and I have 100 watts for my heat flux on the right-hand side. Now that I have a fully assembled global conduction matrix and global load vector, I can apply my boundary conditions. There's just one in this case. T1 is equal to 100 degrees C. And note that this is a non-zero boundary condition. So we're going to have to do, if we apply the method that's used in FE codes, we're going to have to do some motion and changes of the matrix. Let me show you what I mean by that. This is the resulting modified conduction matrix and load vector. And what's happened here is that the first row and column have been changed to all zeros except a 1 on the diagonal. So that the first row now just reads T1 equals 100 degrees C. So I've lost F1. I've removed that information from this problem. But in addition, in the second row, I've changed the right-hand side. And this is because I didn't want to change numerically what the second row represents. So the multiplication of T1 times a negative 6, I moved over to the right-hand side. So now I have a 0 on the left-hand side, and on the right-hand side, I'm going to have 600 watts as an applied load that represents what's coming from that maintaining the temperature of 100 degrees C. Since I'm solving the problem by hand, I can now drop the first row and column and get a 4x4 matrix where I've got my 600 watts that came from moving the term over from the left-hand side, and the 100 watts, which is the given heat flux from the Q term. So this 4x4 matrix, I can solve it, use your solution method of choice, and you get your temperatures at each one of the nodes, T2 through T5. Now I can go back and use that original first equation, the one that I modified, in order to find the flux at the left edge and that equation was that 6 times T1 minus 6 times T2 was equal to F1, which gives me a flux at the left edge of minus 100.2 watts. Then if I want to complete this analysis, I can go back to each element and find the temperature gradients within the element. Again, that's analogous to the strains. We're not going to do that in this case. Instead, I'm going to give you a quick overview of what's different if you want to do a linked thermal stress analysis. Let me talk real quick about a linked thermal stress analysis. This is a fairly common process that you see applied in FEA, where you have a set of temperatures or heat fluxes, and then you're curious how this affects the state of stress in a part. This ends up being a two-stage process where you start out with a thermal analysis, you take the results from that into a stress analysis, and then you finish up and report the combo results at the end. So just walking through that real quick, start out by doing the thermal analysis. So you completely define your problem in terms of thermal loads and conductivity and so on. And then in addition, you're going to have defined upfront the material properties for stress analysis and any physical loads that are applied to the problem. Once you complete the thermal analysis, the resulting temperatures are used to calculate thermal expansions inside the model. So now we have strains at different nodes. You're then going to apply the nodal displacements as an initial strain field in the stress analysis model and apply your boundary conditions and loads for the stress analysis and use the standard stress analysis solution process for final nodal displacements. And at the end, your post-process to display the local displacements, temperatures, strains, and stresses, as well as temperature gradients if you want them. So you have the results of both a thermal and a stress analysis acting on the same geometry that you're reporting out at the end.